My name is David Malan, and I teach a course called CS50, which is our introductory course in computer science for concentrators and non-concentrators alike. And it's a course I myself took, albeit not initially some time ago. Indeed, when I arrived on campus here, I wasn't sure what I wanted to study. In fact, the course catalog itself was completely daunting in so many new fields. And so I, frankly, rather gravitated naturally toward what I already knew. I thought back on high school, and I liked history a bit, and I really liked this constitutional law class. And so when I was flipping through the catalog, I realized, well, maybe government is what I should concentrate in. And I still had this curiosity about computer science, but then and now, to some extent, it was very much this course and more generally this field to beware. I just kind of figured that everyone who's taking the introductory course, CS50, must surely have been programming or taking computer science since they were 12 years old. I remember looking through the glass of window of the computer science classroom in my high school and not really knowing or really caring what my own friends were doing in there. It just seemed so foreign and so unfamiliar to me. And it wasn't until sophomore year that I finally got up the nerve to put my toe in the water. And even then, it was only by enrolling in the class pass-fail, lest I fail the class or get a B in the class. It was my way of getting up the nerve to try what was a very unfamiliar field. And what I realized immediately is that even though I had this perception from high school especially that computer science is programming and writing code and sort of heads down typing away on a keyboard, it's actually much more than that. It really is about ideas, and it's about problem solving. And in fact, it's about using techniques and using ideas that were actually pretty familiar to me already. In fact, one such idea that I'd like to propose is just this today, just one of several ideas, that of abstraction. And abstraction is a fancy way of saying taking something that's really complex and sort of taking a step back and packaging it up in a way that's simpler and that from the top down you can just understand. For instance, I to this day have absolutely no idea how a car works, or underneath the hood, what's inside the engine. If something broke, would have no idea how to fix it. But I've gotten pretty good at using that machine and interfacing with this API, or application programming interface, whereby I get in the chair and I turn the wheel and the thing turns and I push the pedal down and I understand that. And that's what's key. I've abstracted away, as have all of us, we've abstracted away what a car actually is to only needing to understand and care about and master its interface. And in fact, underneath the hood, all of those details can change. It can go from gas to electric, but at the end of the day, other than filling it up, it doesn't really matter to me when operating that device what's going on underneath the hood. And consider some other examples. For instance, what is a country when we talk about a country? Well, in this country, a country is a collection of states. Well, what's a state? Well, a state is a whole bunch of towns. Well, what's a town? A town is a whole bunch of houses. Well, what's a house? Well, it's like 4 walls and a roof. But what's a wall and a roof? Well, it's previously wood and from a forest, or trees that have been turned into 2x4s or the like. So if you get down to the nitty-gritty, you could actually build the thing from the ground up. But we humans generally don't have to care about reconstructing things from those basics. We have the luxury of talking about fairly complex ideas from the top down in a way that just makes them so much more manageable and so much more understandable. Now let's consider things that are a little more technological, like in a computer. At the end of the day, a computer's only input source is like a power cable or maybe a battery. And even if you don't understand how the computer works, you probably know that there's electricity coming out of that cable or battery, so there's like electrons flowing in and out. But at the end of the day, that's the only input to this device. And yet, how can it do so much? How can I write my essays on it and send emails and browse the web and watch videos and listen to music? How did we get to such complexity when the only input at the end of the day is power or electricity? And in fact, what's going on underneath the hood in this case, if we glance there just quickly, is you have all these little switches inside of a computer, transistors as they might be called, millions these days. And they're just little switches that, given some electricity, allow you to turn something on or off. On or off. And a computer scientist would typically call on 1 and would call off 0. And it would seem then that our only vocabulary is zeros and ones. But how do we get from zeros and ones to our emails and to images and to videos and music? Well, let's consider just what we humans know more familiarly is like the number 123. This is just a pattern of symbols, 1, 2, 3. But why is it 123? Think back just a few years to grade school, and you might recall that this is the ones column, the tens column, and the hundreds column. And now how do we get from these columns to an actual value we understand? Well, this is what? 100 times 1 plus 2 times 10 plus 1 times 3, which of course is 100 plus 20 plus 3. There's my 123. Well, it turns out that computers aren't as fancy as we humans. We have 0 and 9 at our disposal typically, so-called decimal system. Computers just have the binary system, bi meaning 2, because they just have zeros and ones, off and on. So in the world of computers underneath the hood, the best we can do is not having powers of 10 up there up top, 1, 10, 100, 1,000, but rather the ones column, the twos column, the fours column, on up. In other words, we can only use powers of 2 in this case. So how in this world might I represent the number we humans know as 0? A computer underneath the hood just turns off 3 switches, so it's off, 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 0, 0, 0. This then is 0. How do we represent using a pattern of switches or lights the number we humans would know as 1? Again, even if you're unfamiliar with computing in binary, at the end of the day, you just need those columns. So what's the pattern? Something, something, something will give me the number we humans know as 1. What's that pattern? 0, 0, 1. It's really as simple as that. Well, how about the number we humans know as 2? How instead would we write this? Not just 0, 0, 1, but rather 0, 1, 0. And if I want to count up further, I can do 0, 1, 1, which now gives me 3. So that's it. That's binary. Now we've gone from this low-level input, just electricity flowing in and out of the device, to being able to represent numbers. And in fact, if I just keep adding more zeros and ones to the left, just like you can make decimal numbers bigger, I can represent any number I might want. But how do you represent an email then? How do you send, for instance, the message hi, exclamation point, or draw something like a flower on the screen as an image that you might see on Facebook or the like? Well, how can we decompose this? Well, you know what? Why don't we just decide as society that this pattern of zeros and ones is just going to represent 3 numbers. In fact, I could do up the math, the 1's place, 2's place, 4's place, 8, 16, 32, and so forth. I can convert those, if I did a little quick math, into these decimal values, which is a little more manageable in my mind. 72, 73, 33. Well, it turns out that humanity just decided some time ago that this number 72 in the context of an email or Microsoft Word or the like is just going to be known as representing the letter H followed by I followed by exclamation point. An arbitrary mapping, but one we humans all agreed upon some time ago. Meanwhile, if I take this same pattern of bits and think of it in the context of like a web browser or Adobe Photoshop or something like that, now these patterns of bits, just by nature of the software I'm using, can be considered in a different context. So yes, it's still the numbers 72, 73, and 33. But what this really means in the context of graphics software is give me a little bit of red, a little bit of green, and a little less blue. Again, 72, 73, and then 33. And this is an RGB triple, red, green, blue. If you've ever heard the expression RGB, combine those 3 colors together, and you get this sort of very, very murky yellow-brown that just barely shows up on the screen here. But now, henceforth, I do not care how murky yellow is implemented. I mean, you really can't see it. I do not care how the word hi is represented. I just want to get real work done and send an email. And I've abstracted away those low-level implementation details, so to speak, such that I know the computer can do it, but I just don't need to care. Now I can function at a higher level, so to speak. So from there, we have, unfortunately, a realization that abstraction is really, really useful. And it's kind of hard to operate without it. And in fact, if you can't take for granted what something is, but instead have to consider lower level how to make it, you realize a challenge. In fact, could I invite one brave prefrosh to come on up on stage and appear before all of his or her potential classmates? You have to be comfortable appearing on cameras and therefore the internet. But if that hasn't set too high of a bar, anyone? There's like 3 hands in this audience, total 4, 5, 6. Now this is a little litmus test. OK, I see bouncing in one seat. So all right, that works. Come on down. And meanwhile, if those of you still seated can pick up that white sheet of paper that has been sitting near you, and if you have not received one, tear someone's in half next to you and grab the pencil we gave you or something else. And what is your name?
Catherine.
This is Catherine. Catherine, this is your future classmates. Come on over here. And what I have for Catherine here is the following. In just a couple of moments' time, I'm going to show Catherine a picture. And Catherine, your charge is not to tell everyone what to draw, but how to draw it. In other words, if you in the audience cannot take for granted what this higher level object is, we're going to find that it's quite hard to function without abstraction. So if you would, into this microphone, describe for the audience exactly how they should draw what only you see.
Are there rules?
That is the only rule.
What it is?
You should not say what it is, just how to draw it. They have a pencil and a sheet of paper to which they can apply that pencil.
OK.
Step 1.
All right. So you have to keep in mind that all of the lines will be equally spaced apart. So first, you should draw a Y in the center of your paper. OK. And then from your right-hand side, from the end of the top right-hand side of your Y, draw a straight line down towards your belly button. Not diagonal, straight line. Make sure it's parallel to the paper. Do the same to the other side so that the entire drawing is symmetrical. And then from the bottom of your Y, draw a line parallel to, OK, so when you first started out with a Y, you have 3 lines, right? So there's one on the top. Oh, no.
It's OK.
Oh, no. OK, I hope no one saw that. OK, so you have one on the top right-hand corner and one on the top left-hand corner. So you want to connect the lines from that you drew parallel to your belly button to the bottom of the Y. Can you guys do that?
All right.
I feel like this is terrible.
This is what, terrifying? Yes, it is now.
OK.
So give them another instruction or two, and then I'll collect some of the answers, and we'll see how close we just got.
OK, and then, so you guys all know what the roof of a house looks like. It's like a triangle. So give your Y a roof of a house so that the Y looks like a square.
Becoming a little less abstract now, but.
Oh, OK. Oh my God.
And how about 2 more instructions to get them to the end?
I don't know what wouldn't give.
Well, then let me do this. Let me get you off the hook here. It's actually a wonderful reinforcement of the message, which is that life is hard without abstraction. But let me, a round of applause for Catherine here. Let me come out and claim. And real fast, if I could just steal a few of the incarnations of these drawings. 1, 2, I'll come down here. Oops, sorry. 3, 4, 5, 6. That'll do. And let's see just how close we came then to what Catherine was encouraging you to draw. And I'll do so by swinging into video mode here. So we have one such drawing. All right, so we have one such drawing. All of them actually look pretty similar. So a little something like that. This one, too, pretty similar. Missing something on the bottom. And this one here. And actually, amazingly, whether by sheer application of those commands or a little bit of a flip of the paper there, we have what was indeed before Catherine, which was this image here, which might jump off the page at you as, of course, hey, draw a cube. But when you don't have that higher level abstraction and actually need to do it from the ground up, that's why this idea of abstraction is just so key. And this then is just one of the ideas that you would learn in the world of computer science, and just one of the ideas that you would learn at the coming fall start. And allow me to conclude here with a look at just some of the other ideas and experience that await you in a course called CS50. Is CS50, Harvard University's Introduction to the Intellectual Enterprises of Computer Science and the Arts of Programming. We got the keys to open paradise, yeah, paradise. Now let's go walking hand in hand. Come on, baby, we can hit.
If you walked in here today, you'd see hundreds of people crowded around their laptops, smiling, laughing, thinking.
bedtime.